show up with like a nostril right here. Student's talking. She thinks she's saying hey, there's a button there. Oh, Miss Juliana. That's so hard.
No, they're not.
The one that kept rolling down the ramp on your electronic group.
For this stack, which is 8 analog, so 20 kilograms per second.
Maybe when you were walking out, did you just like yeah, and someone's walking up. No, I said whatever. She saw.
I know you're talking about Cam, but you said DJ.
Yeah,
so
she was like, I'm like, no. I couldn't say the real reason. I was like, absolutely not.
All right, good afternoon. Welcome again to Math and Modeling Methods. And I think there was some confusion as to when the exam would be. It is on the date that it's posted on the syllabus.
Next Thursday.
So it would be next Thursday, yes. So we have 3 lectures left, basically. And remember that the homework is due on Tuesday of next week. And as soon as you turn in the homework, then I'll post the solutions for you to have them for the test. All right, so are there any questions so far? We covered vector field theory, basically, including all the differential operators and integral identities. We're going to shift gears now to curvilinear coordinate systems, and later, maybe next week or in a couple lectures, we'll kind of recast all these differential operators in generalized coordinate systems. Basically show how you can take the divergency, the gradient, and the Laplace, and the curl on different coordinate systems. Okay, with the forms of those operators that we've derived in class are only for the Cartesian coordinate systems, we should be able to do it for a generalized coordinate system. And when I say generalized or curvilinear, it's basically any coordinate systems. The one that we're used to, obviously, are the Cartesian system, the cylindrical coordinate system for obvious reasons, as engineers actually like cylindrical coordinate systems for the purpose of, for example, analyzing flow in pipes, because pipes are cylindricals. And obviously the spherical coordinate systems, because a lot of things in nature happen spherically. Gravity or the propagation of electromagnetic waves happens spherically, propagated spherically in space. So those are the 3 main coordinate systems that we are probably familiar with and know how to transform from one to the other. However, there are plenty more. There's an infinite number of coordinate systems that we can conceive, and there's 12 known orthogonal ones. Orthogonal meaning that all 3 axes are orthogonal to each other simultaneously. So what we're going to try to do is we're going to develop a framework or formulation so that we can define these coordinate systems in general, show you basically how you go in transforming one to the other, and more importantly, how do you go about solving an integral, for example, in a different space. You can solve a surface integral in the Cartesian coordinate system, and you know how to calculate the Jacobian and project to an area, for example, or you can calculate a volume integral. But what does a volume differential mean in Cartesian coordinates, and what does it mean in cylindrical, or what does it mean in spherical, or what does it mean in general? And then, as I said, well, learn how to calculate and compute these differential operators, gradients, divergencies, curls, and Laplace, in generalized coordinate systems. All right, so a curvilinear coordinates and transformations. So, assuming that we can sketch the Cartesian system like this, and name the coordinates x, y, z like we usually do, and then there are tangent vectors, unit tangent vectors that we call ex, ey, and ec. We call them unit tangent vectors because they're tangent to each of the axes and they're unit in length. So those are the reference vectors that we use to express vector quantities. well, sometimes we call them IJK, depending on the book you use or depending on the instructor. You can transform this to a system that where the coordinates might look curved like this, and then we can call those coordinates perhaps UVW, and then there will be tangent vectors U, EV, and EW. And this system may or may not be orthogonal, meaning that all axes are perpendicular to each other. So we call this UVW system a curvilinear system. And there exists a forward transformation, meaning that U can be expressed in terms of X, Y, and Z. V can be expressed in terms of X, Y, and Z. And W can be expressed in general in terms of X, Y, and Z. So think about U, V, and W being, for example, the cylindrical coordinate system where U, V, and W are R, theta, and Z. And there's a direct relationship between R, theta, and Z and X, Y, and Z. Well, R would be X squared plus Y squared. Theta will be the arctangent of Y over X. And Z will be just Z. The coordinate Z transforms directly into the cylindrical system. Okay? And conversely, there's also a backward transformation. So maybe explicitly you can find a transformation of the kind where X can be expressed as a function of U, V, and W. Y can be expressed as a function of U, V, and W. And Z can be expressed as a function of U, V, and W. Last page. So for example, cylindrical coordinates where U is R, V is theta, and W is Z. These are the three coordinates of the cylindrical coordinate systems, and as I said, it's an important one because, especially for us engineers, a lot of things happen in cylinders. Shafts are cylinders, pipes are cylinders. So a lot of things in mechanical engineering especially occur in cylinders, within or outside cylinders. So there is a transformation, and we can sketch it too. Okay, this is Z, this is Y, and this is X. There's a forward and a backward transformation that leads to the coordinate R, it's called the radial coordinate, the coordinate Z, called the axial coordinate, and the coordinate theta, which is called the tangential coordinate. This one happens to be an orthogonal coordinate system. Okay, it's kind of hard to make that obvious and say, well, theta is always perpendicular to R, which is in terms always perpendicular to Z at any point in space. But then later on today, when we develop the theory and the framework behind this, you'll be able to determine very easily whether a particular coordinate system is orthogonal or not. Okay? Now the forward transformation would be, well, there's an R of x, y, and z, which is square root of x squared plus y squared. There's a theta of x, y, and z, which is simply the arctangent of y over x. And there's a z of x, y, and z. That is just simply z. So the actual coordinate is common in this cylindrical and Cartesian coordinates. All right. And then there's also a backward transformation. Where x of r theta and z is equal to r times the cosine of theta, y of r theta and z is equal to r times the sine of theta, and z of r theta and z is just equal to z. Okay. Well, the first thing we need to, or we want to know about is these tangent vectors. And more specifically, the unit tangent vectors. Can we express them in terms of the tangent vectors in the Cartesian system? So, the tangent vectors to u, v, and w, say given the system x, y, z, and then somewhere here the system w, v, u. And let's say that this is a position vector R. A vector tangent to u will be equal to, and this is, as you can see, not unit vector, it's just AU. A tangent vector to coordinate u is equal to the derivative of the position vector with respect to u. This is a directional derivative in the direction of u. What do we learn about directional derivatives? It's simply the gradient times the vector. Plus 2. So this would be the x du in the x direction plus dy du in the y direction plus dz du in the z direction. And likewise, we can express the tangent vector in the v direction and the tangent vector in the w direction as dr dv, and this one is dr dw, and this will be dx dv in the x direction plus dy dv in the y direction plus dz dv in the z direction. This will be dx dw in the x direction plus dy dw in the y direction plus dz dw in the z direction. Now let's see how this looks like. So as you can see, in order to make up those tangent vectors as a function of the tangent vectors and the xyz system, we need to have the backward transformation. In order to differentiate x with respect to u and y with respect to u and so on and so forth, we need the backward transformation. So you can see, then, as an example, cylindrical backward transformation that looks like x of r theta and z is equal to r cosine y of r theta and z is equal to r sine and z of r theta and z is equal to z. So basically, A in the r direction is equal to the r, which is equal to the x dr in the x direction, plus dy dr in the y direction, plus dz dr in the z direction. And therefore, AR is equal to dx dr is equal to what? Cosine of theta. Dy dr is the sine of theta. And the CDR is just 0. Okay, notice that we're interchanging the notation UVW for R, theta, and Z. Okay, A theta is dr d theta, which is simply dx d theta in the x direction, plus dy d theta in the y direction, plus dz d theta in the z direction. And therefore, A theta, the tangent vector in the theta direction, will be dx d theta, which is minus r sine of theta in the x direction, dy d theta, which is plus r cosine of theta in the y direction, and dz d theta, which is 0. dr dz is equal to dx dz in the x direction, plus dy dz in the y direction, plus dz dz in the z direction. And therefore, if you look at the backward transformation, there's no z in the x backward transformation, so dx dz is equal to 0. 0 in the x direction, plus 0 in the y direction, plus 1 in the z direction. So there are the 3 tangent vectors in this system in relation to the tangent vectors in the xyz system. Alright? Now those are not unit in length. These are just tangent vectors. To make them unit in length, what do we need to do? Just divide each by its own magnitude, right? Well, the first one is already unit because the magnitude of the first one is cosine squared plus sine squared, square root, which is 1. So the first one's already unit. The second one is not unit in length. The third one is already unit in length. So In order to make them unit, we just divide each. Right. So the unit tangent vectors ER is equal to AR divided by the magnitude of AR. And since the magnitude of AR is cosine squared plus sine squared square root, that's already 1, so that stays as cosine of theta EX plus sine of theta EY plus 0 EZ. E theta would be equal to A theta divided by the magnitude of A theta. What is the magnitude of this vector? That would be r squared sine squared theta plus r squared sine squared theta, square root of that. Then we can take the r squared as a common factor. Sine squared and cosine squared is equal to 1. And it will be just the square root of r squared, which is r. So the length or the magnitude of this vector is just r. When we divide that by r, we get the minus the sine of theta in the x direction plus the cosine of theta in the y direction plus 0. And EZ, which is AZ, divided by the magnitude of AZ, is again 0, 0, plus 1. All right. So now we have the 3 unit vectors, tangent vectors, in the cylindrical system. All right. So now for convenience, we're going to switch notations. Switching notation. And we're going to do this for convenience because that way we don't have to specify which one is the coordinate system. We don't need to say r theta phi or r theta z, or we just call the y is a Cartesian system and the x is a curvilinear one. Right? So basically we're going to be switching from a system where this is y1, y2, y3, that's the Cartesian system. This is the position vector r, not the radial direction, just the position vector. And we're going to be moving to a system that looks like x1, x2, and x3. A generalized curvilinear system. Okay? Such that xi is equal to xi of yk. That's the forward transformation. And yi is equal to yi of xk will be the backward transform. So as you can see, we're going to be switching to tensor notation, where the coordinates are not x, y, z, are just x1, x2, x3. Those are the new ones, the curvilinear ones. And the original ones are y1, y2, y3. So we use this indicial or tensor notation or Einstein notation, whichever way you want to call it, it's all the same thing, to make our lives a little easier. All right. So what we want to do is find out what does a differential arc length, a differential surface, and a differential volume mean or are expressed as in the new system, the curvilinear system. And we know that these are invariants. These are properties that we need to respect. The fact that, well, if we measure the length of something in the Cartesian system, that measure should be exactly the same in the curvilinear system. So that's our constraint. So our property is that measure of length, surface, and volume are invariant measures, invariant between coordinate systems. So that's our premise. Whatever we do should get the same. So taking the integral of something in the Cartesian system, the integral over the volume, and doing so in the Cartesian system should yield the same result as doing the same in the cylindrical system. It's just that the differential of volume is going to look a little different with respect to its coordinates. For instance, now we're going to start with differential arc length. What does it mean? Especially when we take the integral over specific arc length. And we're going to call this, see if I can switch my notation to avoid confusion. Yeah, I can switch my notation. I'm going to call it DL, differential arc length. Sometimes it could be DC. I think we use DC in the integrals and the line integrals. Sometimes it's DS, where S is a lowercase s. We're just going to call it DL. All right, so we have our position vector and the Cartesian system, and the differential position vector x, dy, and dz, such that our Cartesian system y1 is x, y2 is y, and y3 is z. In our initial form, y1, y2, y3 is x, y, z. All right. So, a differential arc length square is equal to dr dotted into dr. And therefore, the differential arc length square is equal to dx plus dy plus dz dz. Expressed in initial notations, we have dy1 plus dy2 plus dy3 dy3. Or dl square is equal to dyi dyi. And tensor notation or Einstein notation, repeated index implies summation. Okay? When we have a repeated index, instead of having ij means a two-dimensional tensor or matrix. If we have ii, that's implicitly stating that there's a summation over the index I. It's implicitly saying this is equal to summation between I equal 1 to n of dyi times dyi. We don't need to express it. Okay? Einstein came up with these just to save space, basically. He said we don't want to be writing summation all the time, so anytime we have repeated index, that implies summation. Initial notation, repeated indices implies summation over index, i.e. I equals 1, 2, 3 in this case, 3 dimensions. All right. So that's the differential arc length expressed in Cartesian coordinates. That's just the Pythagorean relationship, right? This is the distance. It's just the square of dx, the square of dy, the square of dz. Now we can express R as an R of the new system, x1, x2, x3. This is the curvilinear system. Therefore, the R will be dr dxi dxi. Notice a repeated index in the same expression, I. That implies, again, I'm going to write it explicitly, but this already implies that this is dx1 plus dr dx2 plus dr dx3 dx3. This implies this. Again, point up, repeat it, indices. Right? So see if we can get an expression for the arc length in terms of x1, x2, and x3. So if you go back a couple pages, see, AU is dr du, AV is dr dv, AW is dr dw. These are the tangent vectors in each of the directions. And you can see them here. These are the tangent vectors in each of the directions. So dr then can be expressed as A1 times dx1 plus A2 times dx2 plus A3 times dx3, which could be expressed in indicial notation as AI dxi. Notice that in indicial notation, the vector over the A is not necessary. A parameter having an index already implies that it is on all three coordinates. So therefore, dl squared, which is equal to dr dotted into dr, is equal to ai dxi. So those two imply summation. Dotted into, let's use another index as dA to avoid confusion, so that we know that this j sums over this j. And therefore, dl squared is equal to ai aj times dxi dxj. Such that this term here, AIAJ, which does not imply summation because it's not the same index, it's just a two-dimensional tensor, is called a metric tensor. And it would be very relevant in the definition of a curvilinear system. It's going to determine many things, especially when a system is orthogonal or not. Okay? So, the L square is the metric tensor, dxi, dxj. This repeated indices implies summation. So we have a double summation from I equal 1, 2, 3, and j equal 1, 2, and 3. So you can express that as the summation over I equal 1, 2, and 3 of the summation of j from 1 to 3. Or you can expand it out and say the L square is equal to G11 times dx1 dx1 plus G12 times dx1 dx2 plus G13 times dx1 dx3 plus G21 dx2 dx1 plus G22 dx2 dx2 plus G23 dx2 dx3 plus G31 dx3 dx1 G32 dx3 dx2 plus G33 dx3 and dx3. Okay, where that G, as you can see, is a two-dimensional tensor. It's a 3 by 3 matrix. That is the cross product of the tangent vectors. Okay. Gij has some properties, that metric tensor. First of all, Gij is equal to Gji. How do we call that property? What does that make that tensor or matrix? When element 3, 1 is equal to element 1, 3? Or 2, symmetric. Okay, so this is a symmetric tensor. And the second and more important property is that if x1 is orthogonal to x2, which is orthogonal to x3, then Gij is equal to 0 for I different than j. So this is the definition of an orthogonal system. So x1, x2, x3 is therefore an orthogonal system. If the off diagonals of the metric tensor are 0, then it is an orthogonal system. So for orthogonal systems, the metric tensor is just a diagonal tensor. It only has values along the diagonal. All right? So basically, if the system x1, x2, x3, whatever it is, can be cylindrical, spherical, parabolic, whatever it is, happens to be orthogonal, all these quantities vanish. All these off-diagonal quantities vanish. The only ones that remain are the diagonal ones. G11, G22, and G33. That's it. So, therefore, for orthogonal systems, dl square is equal to Gii dxi squared. So basically we can take the square root of the left and the right. So dl in a particular direction is equal to the square root of gii times dxi such that this is defined as the square root of each scale factor. So dli is equal to hi times dxi. Right? So the metric tensors, the GIJs, these ones are determined directly from the tangent vectors. So for which we need the backward transformation. And if the system happens to be orthogonal, then we can define the scale factor as the square root of each of the diagonal members of that tensor. In any case, we need the determining metrics from backward transform. Determining metrics. Alright, so in a backward transform, given yk equals to yk of x1, x2, x3. Remember the y represents the Cartesian and the x represents the generalized curvilinear system. So let's say that we have all the relationships. If this is cylindrical, then we have x as a function of r, theta, and z. We have y as a function of r, theta, and z. And we have z as a function of r, theta, and z. dyk is equal to dyk dxi dxi, which is equal to this is a partial, dyk dx1 plus dyk dx2 plus dyk dx3 dx3. The total differential of dyk. So the differential arc length square, which is dyk dot dyk, is equal to dyk dxi times dyk dxj dxi dxj. Notice that I'm using j for one of the summations and I for the other summation. That's just to avoid double repeated index. And as we've already shown, the differential arc length is equal to gij dxi dxj, and therefore the metrics, or the metric tensor gij, is simply from the backward transformation dyk dxi dyk dxj. So if we have the backward transformation and we can explicitly differentiate with respect to each of the coordinates, that will give us the whole tensor. And if we explore that tensor and it happens to be symmetric, well, it's always symmetric, but if it happens to be diagonal, all the off diagonals being equal to 0, then that system is orthogonal. For example, we can calculate element 1, 1 of this tensor. That will be, notice that it's summation over all the cases. It's a repeated index, so that would be dy1 dx1, dy1 dx1, plus dy2 dx1, dy2 dx1, plus dy3 dx1, dy3 dx1. That's such that I is equal to 1, j is equal to 1. And again, k is repeated, and therefore you add up over all the range. Okay. All right. So, let's look at an example. Again, we'll go back to the usual cylindrical system, which we know is an orthogonal system, but now we can prove it. What is the backward transformation of the cylindrical system? y1, y2, y3 as a function of x1, x2, x3. It would be x1 cosine of x2, x1 cosine, sine of x2, and this will be just x3. Right? I'm just changing notation. Remember, this is x, y, z. This is r, this is theta, and this is z. In the cylindrical coordinate system, such that x1 is equal to r, x2 is equal to theta, x3 is equal to z. Alright, so let's try to determine all 9 elements of the tensor Gij. Well, we know that there's only 6 because it's a symmetric tensor, right? So we don't need to determine, if we determine 1, 3, we don't need to determine 3, 1 because it's going to be identical no matter what, regardless of whether it's orthogonal or not. Let's start with the diagonals. G11 is from here, dy1 dx1, dy1 dx1, dy2 dx1, dy2 dx1. So we need to differentiate this one with respect to x1. That will be the cosine of x2 times the cosine of x2. This is parentheses. Then we need to differentiate this one with respect to x1. That would be sine of x2, sine of x2. And then we need to differentiate this one with respect to x1. This will be 0, 0. And what do we get? Cosine square of x2 plus sine square of x2. What's that? 1. G22, it would be this one with respect to x2. That would be x1 minus x1 sine of x2 minus x1 sine of x2. This one with respect to x2, that would be x1 cosine of x2, and this will be x1 cosine of x2, and then y3 with respect to x2, 0, 0. So we have sine square of x2, cosine square of x2, the common factor x1 squared. On both sides, positive. That's x1 squared. G33. It will be this one with respect to x3, that's 0, and this is 0. This one with respect to x3, that's 0, 0. And the last one with respect to x3 is 1 and 1. So that would be 1. Let's compute the off diagonals. G12. G12. Alright, so it would be this one with respect to x1 times this one with respect to x2. Right? So it would be this one with respect to x1 will be cosine x2, and this one with respect to x2 will be minus x1 sine of x2. Agreed? It will be the differential of y1 with respect to x1 and the differential of y1 with respect to x2 plus the differential of y2 with respect to x1 would be the sine of x2 times the differential of y2 with respect to x2. X1, and then with respect to x2, it would be x1 times the cosine of x2. And then the differential of y3 with respect to x1 is 0, and with respect to x2 it's also 0. And what do we get out of these? Minus x1 that multiplies cosine of x2, sine of x2. And this one is x1 that multiplies sine of x2, cosine of x2. This one is negative, this one is positive, this one is 0. What do we get? All goes away. Let's do 1, 3. So the differential of y1 with respect to x1, it would be cosine of x2, and with respect to x3, 0. The differential of y2 with respect to x1, it will be the sine of x2, and with respect to y3, it will be 0. And the differential of y3 with respect to x1 is 0, and with respect to y3, with respect to x3, is 1. So it's all 0 times 0 times 0, you get 0. y23, the differential of y1 with respect to x2 is minus x1 sine of x2, and the differential of y1 with respect to x3 is 0. Plus the differential of y2 with respect to x2 would be x1 cosine of x2 times 0, plus the differential of y3 with respect to x2 is 0, and with respect to x3 is 1. And that all gives you 0. So as you can see, this tensor Gij looks like 1, 0, 0, 0, x1 squared, 0, 0, 0, 1. So this is diagonal tensor. Therefore, x1, x2, x3 is orthogonal. So we can express this transformation as well. x1 is equal to r, x2 is equal to theta, x3 is equal to z. GRR is equal to 1, G theta theta, which is G22, theta theta, is equal to R squared, and GZZ is equal to 1. These are the metric tensors, and the scale factors, which are the square root of these. HR is equal to 1, H theta is equal to R, and HZ is equal to 1. just a matter of keeping up with the notation, and if we use this framework, we can express the transformation, metric tensors, and scale factors for any coordinate system, curvilinear system, not just obviously this cylindrical. The arc length square is equal to dii times dxi square, and that would be dr squared times 1 plus r squared d theta squared plus dz squared. Okay? dLr is equal to dr, dL theta is equal to r d theta, and dLz is equal to dz. The metric tensor times the corresponding Alright? So differential length in the radial direction is just dr, differential length in the tangential direction is r d theta, differential length in the axial direction is just dz. So for example, how do we implement this in an actual application? If we calculate the arc length, L is the integral from P1 to P2 of dl. Let's say we want to calculate the length of a chord in space. That length is an invariant, whether we measure it in the Cartesian system or we measure it in the cylindrical system. At the end of the day, that length is going to be the integral from P1 to P2 of dl, which is the square root of all this stuff. dr squared plus r squared d theta squared plus dz squared. And we can parameterize r, theta, and c. Remember, r, theta, and c, we're trying to calculate the arc length in space. So we have the relationships of, say, let's say a parameter c, such that r is equal to r of c, theta is equal to theta of c, and c is equal to z of z. So we have the equations, the parametric equations of a chord in the r, theta, and c dimensions. And therefore, the r is dr, dc, dc. The theta is equal to the theta, dc, dc. And dz is equal to dc, dc, dc. So this integral for the total arc length is the integral from position 1 to position 2 of the square root of the r dc squared plus r squared times the theta dc squared plus dc squared times dc. Right? So what in the Cartesian system in Pythagoras will be dx squared plus dy squared plus dc squared, that's the length of the arc length. In the cylindrical system, we have that r squared right in the middle of things, right there. Okay. Let's continue. So we did 1 differential arc length, 2 differential areas for surfaces. So in the, I'm going to call this ds. So in the Cartesian system, x, y, z. So right here, right here, right here. This one, let's say that this is dy, this is dx, and this is dz right here. This right here is a differential surface parallel to z, which is dx dy. This is a differential surface parallel to x, which is dy dz. And this is a differential surface parallel to y, which is dx dz. There's a forward transformation and there's a backward transformation. And let's say now that this is W, this is V, and this is U. This is dW, this is dV, and this is du. Right? So right here we have a differential surface parallel to W, which is equal to the Jacobian of W times du dV. This is a differential surface that is parallel to U, which is the Jacobian in the U direction times dV dW. And right here we have the differential surface parallel to V, which is the Jacobian in V, times du dW. All right? So the differential surface in a specific plane, parallel to a specific plane, would be the magnitude of the cross product of the tangent vector j times the tangent vector k times dxj dxk. I'm going to use the identity A cross B is, or times C cross D is equal to A dot C B dot C minus A dot D B dot C. This is a dot, not a minus. So the magnitude of AJ cross into AK is equal to the square root of AJ cross into AK dotted into AJ, cross into AK. So using this identity, AJ cross into AK is equal to the square root of AJ dotted into AJ times AK dotted into AK minus AJ dotted into AK times AJ dotted into AK. Notice that this AJ cross AK is that Jacobian. This is Jacobian of the transformation in the I direction is equal to, from here, GJJJ GKK minus GJK squared. This is Jacobian of the surface transformation. These are usually the most difficult ones, the transformation of the differential surfaces. So, therefore, a differential surface I parallel to a axis I is equal to the square root of GJJ GKK minus GJK squared dxj dxk. Right? So if the system x1, x2, x3 is orthogonal, then GJK is equal to 0 for J different than K. And therefore, dSi is equal to Hj, Hk, dxj, dxk. That's only for orthogonal systems. All right? So, this will serve us to know what the differential surfaces mean when we take an integral in cylindrical coordinate systems or in spherical coordinate systems. Thus saying the differential area or surface is not directly dr d theta, for example, like it is dx dy in Cartesian systems. So we need to use the scale factors. If the system is orthogonal or not, we need to use the metric tensor if the system is not orthogonal. All right, so when we come back on Thursday, we'll do some examples. We define the differential volume, which is a simpler version of these. And then we are going to define how to do the operators, differential operators in generalized coordinates. And that should be enough. By the end of the lecture on Thursday, you should have enough to be able to solve all the problems in the homework. Okay? Yes?
What section is this in the SIL book?
In the SIL book. I'm going to have to get back to you. I don't know exactly what chapter it is. It must be, yeah, it must be 7. It must be on the same exact chapter where you have the introduction to vector field theory. and there should be a section on that chapter that talks about curvilinear systems. Okay. All right.